So in the previous video, we have derived a beautiful equation for continuous time Fourier series which says that we can express an input signal in terms of complex exponentials. Now, if you look carefully into the equation, you can see that there is a term called AK, which is nothing but the coefficients of the complex exponentials, with which value we have to multiply our complex exponential. That is what the coefficient says. Now, how to find out these coefficients? There are some mathematical procedures for that, how to find out these coefficients of the complex exponentials, right? So let us go into the derivation of finding out the coefficients of these complex exponentials, and which will lead to another equation known as the analysis equation. So we will have a pair of continuous time Fourier series equations. One is known as the synthesis equation and second one is the analysis equation. The synthesis equation will help us to synthesize any signal using the complex exponential, that is harmonically related complex exponentials, and the analysis equation will help us to analyze any given signal in terms of complex exponentials. So without wasting time, let us go into the video and watch how it is done mathematically.
We have the continuous time Fourier series equation x of t is equal to summation k equal to minus infinity to plus infinity ak e power j k omega 0 t. So what this equation says? This equation says that any signal x of t can be expressed as a linear combination of harmonically related complex exponentials, right? Now our question is how to find out these coefficients. So these are known as the coefficients, right? Coefficients. So how to find out the values of these coefficients in this equation? That is also required for us, right? So this can be done using some mathematical procedures. So I am just showing the derivation. How can we find out the coefficients ak and what is the derivation behind, right? This, okay. So what I'm going to do is that I'm going to multiply the equation x of t, right? X of t, this is our equation. X of t is equal to summation k equal to minus infinity to plus infinity ak into e power j k omega 0 t. I am going to multiply both the sides of the equation using e power minus j n omega 0 t, right? E power minus j n omega 0 t. Since I am multiplying on the both the sides of the equation, so its value will not change, right? E power minus j n omega 0 t. Now I am going to integrate both the sides of the equation within the range 0 to t. The values will not change. I am doing the integration on the left side and the right side. Now I am going to concentrate on the right side of the equation. What I am going to do is that I am going to concentrate on the RHS of this equation, right? RHS part of this equation. So first step, I am going to interchange the integration and summation. So first thing is what I will do, I will take the summation outside. K is equal to minus infinity to plus infinity, right? And I will take the integration inside. I am taking the integration inside 0 to t0. And what is the terms there? Ak into e power j, and here also e power j omega 0 t is there. Here also e power j omega 0 t is there, and there is a k and n. So if I combine together, how can I write? J into k minus n omega 0 t dt. So compared to this integration, ak is also a constant, so I can take that also outside. So what I can do, I can take the ak outside. So this is the integration, so I can take ak outside of the integration, and what is remaining inside? E power j k minus n omega 0 t. So now we are going to concentrate on this particular integral on the RHS of this equation, that is integral 0 to t0 e power j k minus n omega 0 t dt. So this is the integral under our consideration, right? Now using Euler's identity, you can express it as integral 0 to t0 cos k minus n omega 0 t plus j sine k minus n omega 0 t. So I have to put a bracket here, right? So this integration I can do by taking the integration to each of the terms because it is a plus sign here. So I can write it like integral 0 to t0 cos k minus n omega 0 t dt, right? So here also dt is there, dt plus the second integral 0 to t0, so j I can take outside, right? Sine k minus n omega 0 t dt. So this is how the integral now changed its form, right? Now you can see that when k and n are equal, so assume that when k is not equal to n, right? In the beginning, let us assume that k is not equal to n. So when k is not equal to n, this is a cosine function, this is a cosine function, right? This is a cosine function, and this is a sinusoidal sine function, right? This is a sine function, right? When k is not equal to n, this is a cosine function, this is a sine function, right? And if you carefully observe, you can see that we are integrating within the range 0 to t0, right? We are integrating within the range 0 to t0, right? And that is one period, actually one period, right? So we are integrating within the range one period. Okay, so we have already discussed that integration is nothing but integration, right? So integration is nothing but area under the function of area under the curve, right? Area under the function, area under the function. So in that case, if you find out the area under the function of sine wave and cosine wave for a period, its value will be 0, right? Both sine function and cosine function is having a positive region and a negative region. If you take the area over one period, it will cancel each other and you will get 0, right? So that is the condition. When k is not is equal to n, this integral don't have any value because it will become 0 for both cosine and sine wave. When k is equal to n, what happened to this equation? This equation will become integral 0 to t cos 0 into omega 0 t dt, right? Plus integral 0 to t sine 0, because k and n are equal, so k minus n is 0. Here also k minus n is equal to 0. Sine 0 omega 0 t dt, right? You can see that sine 0 is anyway 0, so this doesn't have any value. Now what is remaining here? Here it is remaining only 0 to t cos 0 is 1, right? So 1 dt. So we have started from an equation integral 0 to t0 x of t into e power minus j n omega 0 t is equal to summation k equal to minus infinity to plus infinity ak into integral 0 to t0 e power j k minus n omega 0 t dt, right? And through some mathematical manipulations, we have seen that it has value only when k is equal to n, and that is nothing but t0, right? So you can substitute that result into this equation, right? So what is our LHS? LHS is 0 to t0 x of t into e power minus j n omega 0 t, which is equal to, it has some value only when k is equal to n. So this summation don't have any value now, because when k is having some other values from minus infinity to plus infinity, it does not have any role, right? So now the summation does not exist there, right? So it has only value when k is equal to n, right? So we can call it as a n into t0, right? We can call it as a n into t0, and from this we can also see that it is ak into t0, because n and k are equal, right? Ak into t0. So from that we can get a relation for ak. Ak is equal to 1 by t0 into, because we have to take this t0 into the denominator, 1 by t0 into integral 0 to t0 e power minus j n omega 0 t dt. So this equation we can get for the coefficients ak. So using this equation we can find out the coefficients of CTFS. Now we have two equations. What are the equation? We have the first equation x of t, right? Any signal x of t can be expressed as a linear combination of harmonically related complex exponential, right? Harmonically related k omega 0 t, right? Harmonically related complex exponential. So this equation is known as the synthesis equation, right? Synthesis equation of CTS. Why it is known as a synthesis equation? Because if we know these terms, if we know these CTFS terms, we can create or synthesis our signal x of t using these terms, right? So that is why this particular equation is known as the synthesis equation of CTFS. We have also derived another equation just now, that is ak is equal to 1 by t0 into integral 0 to t0 x of t into e power minus j n or k omega 0 t, k omega 0 t dt, and this equation is known as the analysis equation. This equation is known as the analysis equation, right? This equation is known as the analysis equation. Analysis equation of continuous time Fourier series or CTFS. This is known as analysis equation because this particular equation analyzes what is the weight or what is the amplitude of each of the harmonics, right? So actually this ak is the multiplier for e power j omega 0 t. So it is determining the amplitude of the harmonics, right? So this equation is known as analysis equation because it analyzes the weight of each harmonic of the sinusoidal signal that are present in the arbitrary signal x of t, right? And these coefficients are also known as Fourier series coefficients, right? Fourier series coefficients of a continuous time periodic signal are also known as spectral coefficients, right? This is known as spectral coefficients because if you plot this ak on a graph, right, with respect to frequency, if you plot these ak values on a graph, we can know that what are the frequencies present in the signal x of t, right? What are the frequencies present in the signal x of t? So because of that we are getting an idea of the frequency spectrum, what all frequencies are there in the signal x of t, right? So because of that reason this is known as the spectrum, and these coefficients are known as the spectral coefficients of the continuous time Fourier series, right? So these two equations, analysis equation and synthesis equation, are very important in solving so many problems in signals and system.
I hope you got a clear idea about the synthesis equation and analysis equation, which is used to synthesize signals and analyze signals. For example, let us assume that we wanted to produce the violin sound or tamburu sound from an electronic keyboard or electronic piano. Now we wanted to go to the violin and we have to record the sound and we have to analyze it. What are the frequency components present in this particular violin sound? That is known as the analysis, right? Now using this information we have to synthesize this signal using the individual harmonically related components inside the electronic keyboard. That's why when you press a button it is producing the sound similar to violin. It's not exactly equal to violin sound, similar to violin sound, because wherever there is an approximation there is an error. So this is the best example of the analysis and synthesis of continuous time Fourier series.